Yeah, welcome. So from this session, we'll be moving to a new topic, which is deadlocks. We'll be discussing deadlocks under these headings. System model, that is under which circumstance deadlock will occur, and deadlock characterization. What are the conditions that has to be satisfied if you want to call a system as deadlocked? That we'll be discussing under deadlock characterization. Then we'll be discussing several methods of handling deadlocks like deadlock prevention, deadlock avoidance, and deadlock detection. And also we'll be discussing recovery from deadlock. Okay, that is how the system can recover from a deadlock. The objective of the topic is to first to provide a description of the deadlock. Okay, so basically deadlock avoid the processes from completing their task permanently is until you reboot the system. So what is deadlock? Why that condition occurs? So that we will understand, and then we will discuss several methods for preventing and avoiding deadlocks in a computer system. Fine. Let us move to the topic. So we'll start with a system model where we'll try to understand the concept of deadlock. So as you know, in a multi-processing, in a multi-programming system, there will be many processes running in the computer, and the system consists of different types of resources. And the processes will be competing for different resources. Each process will compete for a different resource. And there are different types of resources. Like resources includes CPU, time, memory space, IO devices. All these are examples of resources. Even if you consider semaphore is also a resource, because semaphore is basically a it's a locking mechanism which is used to avoid the problem of critical section. Okay, but that is also a resource. Semaphore is also a resource. Mutex locks is also a resource. So all these are the different types of resources a computer may have, and each resource may have more than one instances. Okay, it is not that all resource should have only one instance. That depends on the situation or the computer you are using. Sometimes a resource Ri may have Wi instance, and this Wi may be equal to one or it may be more than one also. For example, if my computer is connected with two printers, then it means that I have two instances of printers. Okay, and if my computer is connected with three scanners, then it means that I have three instances of scanner. So each resource can have more than one instance. If a process want to acquire a resource, first it should place a request to the operating system. First it will place a request to the operating system that I want so and so resource. Then it will get the resource, or the operating system will allot the resource to that particular process, and the process will use that resource, and once its task is completed, it will release the resource. So this is how normally uh, the process request and release the resource. Okay. Okay. Now let us see why deadlock occurs and what is an example for a deadlock. Assume that in my computer there is one printer and one scanner. Okay. So there is a PC or a laptop which is connected with one printer and one scanner. Okay, so it means there is one instance of printer, there is a resource printer, And how many instances we have? We have only one instance. Similarly, there is a resource scanner, and how many instances we have? We have only one instance. So there is one instance of printer and one instance of scanner. Okay. Say, say currently two processes were running in the system. Let it be P1 and P2. These are the two processes that were running in the system. Process P1 and process P2. Okay. Let us assume that this printer resource is already issued to the process P1. Okay, the printer is given to the process P1 and the scanner is already given to the process P2. Scanner is already given to the process P2. Okay, now say that the process P1 needs scanner. The process P1 needs scanner before releasing the printer. This is the situation. Process P1 needs scanner before releasing the printer. Similarly, process P2 needs printer. Process P2 needs printer before releasing the scanner. Okay, now what will happen? P1 is holding the printer and it is waiting for scanner. P2 is holding the scanner and it is waiting for the printer. So this concept is called a circular wait. So both the process P1 and P2 will keep on waiting that the other resource will be available, but the other resource will never be available. So this situation is one example for deadlock. Okay. So now this two process will halt permanently until you reboot the system or you restart the system. Okay. So this problem is called as deadlock. Okay. Similarly, we can give more examples for deadlock. So basically it means that there are, if you have n processes and each process is holding a resource and it is waiting for another resource from another process, and if it is a circular wait, then it will lead to something called as deadlock. Okay. So this is the whole idea of deadlock. Okay. So with this understanding, let us now uh, characterize deadlock. Okay. So deadlock will occur if the if four conditions were held simultaneously. Deadlock will occur if these four conditions are held simultaneously. What are they? First is mutual exclusion. You know what is mutual exclusion? Mutual exclusion means there is a shared resource which can be accessed by only one process at a time. If one process is accessing the shared resource, then others will be waiting. So deadlock, so one of the conditions to ensure deadlock is mutual exclusion. Okay, only if all the four conditions are satisfied, you can say that it is deadlock. Otherwise, you cannot say it is deadlock. Okay, even if one condition is not there, you cannot call it as a deadlock. Okay, only if all the four conditions are satisfied, we can call it as a deadlock. So mutual exclusion, if mutual exclusion is there, that is one process is using the resource and other processes are waiting. So that is called as mutual exclusion. One process is using the shared resource and other processes are waiting. If mutual exclusion is in place, then there is a chance for deadlock. The second is hold and wait. Hold and wait means a process P1 is holding some resource Rj. The process P1 is holding some resource Rj. It is already holding a resource Rj and it is waiting for some other resource Rk, and it won't release Rj until it receives Rk. So this is called as hold and wait. That is, the process is is holding one particular resource, and without releasing that resource, it is waiting for another resource, and it is not going to release the other resource until it get this resource. So this concept is called as hold and wait, which is the second condition for deadlock. The third condition is no preemption. So no preemption here in the sense, previously we have discussed preemption process and non-preemption process, but here no preemption in the sense the resource cannot be taken away from a particular process uh, by the operating system. That is called as no preemption. No preemption means If a resource is allocated to a particular process, then the process should voluntarily give up the resource. Until the process does not voluntarily give up the resource, the operating system cannot forcefully take the resource out from the process. So that is called as no preemption. So if no preemption is there, okay, so that is the third condition. If no preemption is in place. The fourth is circular weight. Okay, circular weight. So in the previous example, we have discussed circular weight. So more formally, we can define circular weight as something like this. Say, for example, we have many processes from P1, P2, P3 up to Pn. Say we have processes, all these processes are available in the system actively, P1 to Pn. Okay. Now let us say that P1 is holding a resource and it is waiting for a resource from P2. P1 is holding a resource and it is waiting for a resource from P2. P2 is holding a resource and it is waiting for a resource from P3. P3 is holding a resource and it is waiting for a resource from P4. Like that it continues. Similarly, Pn minus 1 is holding a resource and it is waiting for a resource from the process Pn. Okay. And Pn is holding a resource and it is waiting for a resource which is held by P1. Okay. So, so it means P1 is holding a resource and it is waiting for a resource which is currently held by P2. P2 is holding a resource and it is waiting for a resource which is currently held by P3. P3 is holding a resource and it is waiting for a resource which is currently held by P4. This continues. Pn minus 2 is holding a resource and it is waiting for a resource which is held by Pn minus 1. And Pn minus 1 is holding a resource and it is waiting for a resource which is held by Pn. And Pn is holding a resource and it is waiting for a resource which is held by P1. So this feature is called a circular weight. Okay. So if all these features are there, if all these conditions are there, then you can say that the system is in deadlock. Even if one of the condition is not there, then you cannot call it as a deadlock. This is how circular weight is formally defined. There exists a set of process P0, P1 up to Pn. P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. Like this, it goes on, dot, dot, dot. And Pn minus 1 is waiting for a resource that is held by Pn. And Pn is waiting for a resource that is held by P0. So if all the four conditions were satisfied, then we call it as a deadlock. Okay, so mutual exclusion should be satisfied, hold and wait should be satisfied, no preemption should be satisfied, and circular weight should be satisfied. If all these are satisfied, then you can say that the system is in deadlock state. Even if one of the condition is not satisfied, then you cannot call it as a deadlock. So this is how deadlock is characterized. Fine. So next, let us discuss a concept called resource allocation graph. See, the way in which the processes were allocated to the resource can be represented through a graph. And this graph is called as resource allocation graph. So this graph contains, so typically any graph will have vertices and edges. So this graph has two types of vertices and two types of edges. Okay? This is a directional graph. It means there will be an arrow from one vertex to another vertex. So, so any graph will have vertex and edges. So this graph has two types of vertices. Okay. So what are the vertices? So these vertices, uh, yeah. So vertices are represented as V and edges are represented as E. And there are two types of vertices. All the processes in the system are represented as vertex. Okay. The first type of vertex is process. All the processes in the system are represented through vertex. And processes are represented through the alphabet P. Okay, so P1 represents process 1, P2 represents process 2, and so on and so forth up to Pn represents process n. So process represents vertex. Okay, so this is process is one type of vertex. So as I have mentioned, there will be two types of vertex. Okay, so the first type of vertex is process. The second type of vertex is resources. All the resources in the system were also represented through the vertex, and the resources are represented through the vertex R. That is, R1 represents resource 1, R2 represents resource 2, and so on and so forth up to Rm represents resource M. Okay. And edges are also of two types. So there are two types of edges. So one is called as assignment edge. One is called as assignment edge. If a resource Rj is already assigned to a process Pi, then there will be a edge from Rj to Pi. If a resource Rj is already allotted to the process Pi, then there will be an edge from Rj to Pi, and that edge is called as assignment edge. It means this resource is already allocated to the process. In this case, the arrow will be from Rj to Pi. The arrow will point Pi. So this is called as assignment edge. The second type of edge is called as request edge. If a process Pi is requesting for a resource Rj, it means the resource Rj is not yet allocated to the process Pi, but is just placing a request. Then there will be an arrow from Pi to Rj. So that is called as request edge. Okay. So resource allocation graph contains two types of vertexes. One is the set of processes which are represented as PIs. The other one is set of resources which are represented as RIs. And, and it has two types of edges. The first one is assignment edge. If a resource is already assigned to a particular process, then there will be an edge from that particular resource to that particular process. The arrow will point towards the process. Okay. So that edge is called as assignment edge. If a process is requesting for a resource, then there will be an edge from the process to the resource. Okay, that is, if a process P is requesting a resource R, then there will be an arrow from P to R. Now the arrow will point towards R. Okay, so it means the process is requesting the resource, it is not yet allocated. Okay, so these are some of the symbols that we use in the resource allocation graph. So processes are represented by circles. These are vertex basically, and resources are represented by squares. Okay, and inside the square there will be some dots. Dots are subsquares, which is used to represent the number of instances of a resource. So here you can say this, there is a resource and there are four squares inside, which means that this resource has four instances. Okay, and pi represents process, rj represents resource. So pi, there is an arrow from pi to rj, so it means that pi is requesting a resource rj. Pi is requesting an instance of the resource rj. Okay, here you can say that one of the instances of rj is given to pi. One of the instances of rj is given to pi, which means that the resource, one of the instances of the resource rj is already allocated to pi. Okay, or pi is holding an instance of the resource rj. So these are some of the symbols which we use in the resource allocation graph. So before discussing the resource allocation graph, if you are aware of the symbol, it is quite good. So that's what we are discussing here. Okay, so basically why we use resource allocation graph? So we use resource allocation graph to detect whether the system is in a deadlock state or not. So how to detect? After drawing the resource allocation graph, if the graph contains no cycles, after drawing the resource allocation graph, if the graph contains no cycles, then it means that there is no deadlock. Okay. After drawing the resource allocation graph, if there is no cycle in the graph. Cycle means, say there is a node here and this node is pointing to some other node here, okay, and again this node is pointing to some other node here, okay? And again this node is pointing to the original node here. So here there is a cycle, okay. Say this node is A, so A, and this is B, and this is C. So in this case A is pointing to B and B is pointing to C and C is again pointing to A. So that is a cycle, okay. But assume it is this way. A is pointing to B, okay. A is pointing to B and B is pointing to C. B is pointing to C and C is not pointing to A, but again A is pointing to C, okay. So this is actually not a cycle, because here if you go in this direction, A is pointing to B and B is pointing to C, but again C is not pointing to A, so there is no cycle here. If you come this direction also, A is pointing to C, that's all, and C is not pointing to B or anything else. So this is not a cycle, whereas this is a cycle, okay. So what you can infer from the resource allocation graph, in the sense, if there is no cycle in the graph, then you can confirm that there is no deadlock, okay, or the operating system can confirm that there is no deadlock, okay. What if there is a cycle? So if the graph contains cycle, then there are two possibilities. If the graph contains a cycle, then there are two possibilities. The system might be deadlocked or it might not have been deadlocked, okay. If there is no cycle, then you can confirm that there is no deadlock. But if there is a cycle, then you cannot confirm. There may be deadlock or there may not be deadlock, okay. So how to know if there is a deadlock or not? If there is a cycle and if all the resources has only one instance, if there is a cycle and whatever the resource that are involved in the cycle, okay, whatever the resource that were involved in the cycle, and and those resources has only one instance, then you can confirm that there is a deadlock, okay. I think it's clear. If there is a cycle, then you have to check what are the resources that are involved in the cycle, and if all the resource has only one instance of that particular resource, okay, there is only one instance, it means the resource has only one instance, it does not have more than one instance. In that case you can confirm that there is a deadlock, okay. But if there is a cycle and the resources involved in the cycle has multiple instances, they have several instances per resource type, then there is a possibility of deadlock, but we cannot confirm. Then there is a possibility of deadlock, but we cannot confirm. You have to really look into it to confirm whether there is a deadlock or not, okay. So this is the usage of resource allocation graph. After drawing the resource allocation graph, if there is no cycles, then you can confirm that there is no deadlock. If there is a cycle, then you have to check what are the resources that are involved in the cycle. And if all those resources only one instance per resource type, then it means that there is a deadlock. But if those resource has multiple instances, then there is a possibility of deadlock, but you have to further investigate the system to know whether really there is a deadlock or not. Now let us discuss some examples of resource allocation graph with cycle and without cycle. Okay. So this is a resource allocation graph. So you can, as we have already discussed, resource allocation graph contains vertex and edges. All the processes and resource are represented through vertexes. Okay. So here there are three processes, P1, P2, and P3. And there are four resources, R1, R2, R3, and R4. For resource R1, there is only one instance. For resource R3, also there is only one instance. But resource R2, there are two instances of resource R2. And there are three instances of resource R4. Okay, so this is the situation. So this graph, what it says in the sense, the resource of one of the instance of the resource R2 is already assigned to the process P1. Okay, one of the resource, one of the instance of the resource R2 is already assigned to the process P1. Okay, and P1 is requesting the resource R1, and P1 is requesting the resource R1. Okay, and R1, there is only one instance of R1 available, and that is already allotted, that is already assigned to P2. The one instance of R1 is already assigned to P2, and the other instance of R2 is also assigned to P2. It means P2 is currently holding two resources. One is R1, the other one is R2. Okay, and P2 is requesting the resource R3. There is only one instance of R3, but still P2 is requesting the resource R3. So P1 is holding R2 and it is requesting R1. P2 is holding R1 and R2 and it is requesting R3. And the process P3 is holding the resource R3. There is only one instance and that instance is held by R3. So that instance R3 is held by the process P3. Now let us first understand whether this graph is having a cycle or not. Okay, let us see. Let us come from process P1. Okay, let us try to understand is there is any cycle or not. So P1 to R1, you can say there is something. R1 to P2 is there is an arrow. Okay, but there is nothing from P2 to, there is nothing from P2 to R2. Okay, so in this way there is no cycle. In this direction there is no cycle. Okay, so in this direction there is no cycle. So what you can do in the sense, let us see in any other direction is there is a cycle or not. So from P2 again you can go back to R3. Okay, fine. From R3 again you can come to P3. Okay, but but after that there is nothing. P3 is not, so again you cannot come back here. There is no arrows here. So basically, you can also check other possibilities. If you come from P1 to here, there is no possibility. Okay, if you take P2 to here also, P2 to R3 and then R3 to P3, right? So basically this graph does not have any cycle. Okay, so this graph does not have any cycle. So here there is no deadlock. Here there is no question of deadlock. Okay, why there is no question of deadlock means because only R3 is, only P3 is only holding R3. Okay, so maybe after some times, after X amount of time, P3 will release R3. Once P3 releases R3, P2 will get the resource R3. Now P2 got all the three resources R1, R2 and R3. Then P2, once it gets all the resources, it will complete at say some time x plus t naught, because P3 completed at time x, so it may complete at x plus t naught. So at x plus t naught, P2 will release R2, R1 and R3, everything. And then P1 is waiting for R1. So P1 will get that R1 and eventually it will also complete. So basically this is not at all a deadlock situation, and that you can understand from the resource allocation graph also, as there is no cycle, there is no deadlock here. Okay, so let us here there is a deadlock. Okay, so now let us see this particular case, what happens here. So here the process P1 is holding the resource R2. So here also we have the setup is same. There are three processes and there are four resources R1, R2, R3 and R4. R1 and R3 we have only one instance, but R2 we have two instance and R4 we have three instance. So P1 is holding one instance of R2 and it is waiting for R1. And P2 is holding one instance of R2 and one instance of R1. R1 there is only one instance and it is waiting for R3. P3 is holding one instance of R3 and it is waiting for R2. P3 is holding one instance of R3 and it is waiting for R2. Okay, so here let us see there is a cycle or not. Let us start from P1. P1 to R1, yes, there is an arrow. R1 to P2, yes, there is an arrow. P2 to this way there is no arrow. Okay. So let us go this way. P2 to R3, yes, there is an arrow. R3 to P3, yes, there is an arrow. P3 to R2, yes, there is an arrow. And R2 to P1, yes, there is an arrow. So there is a cycle. So this is a cycle. Okay, this cycle comes like this. It goes here, again it come back to here, again it goes here, it come like this. So there is a cycle. Okay, so this is, so sometimes it may have more than one cycle also. Okay, so this is one cycle. Let us see is there any other cycle or there not. So you say, let us start from P2. Let us start from P2. Say if you start from P2, you can also have another cycle. P2 to R3, okay, and then R3 to P3, and then P3 to R2, and again from R2 to P2. So this is another cycle. So basically there are two cycles are here. Okay. So this graph contains two cycles. So there are possibilities for deadlock. Okay. Because that is what our rule says. If there is no cycle, then there is no deadlock. If there is a cycle, and if all the resource involved in that cycle has only one instance of the resource, then there is a deadlock. But if there is more than one instance, then there is a possibility of deadlock. Here R1 there is only one instance, R3 there is only one instance, but R2 we have two instances. So there is a possibility of deadlock. But how can we confirm whether there is a deadlock or not? In this case, it is surely a deadlock because none of these instances were free. Even though R2 contains two resources, even though R2 contains two instances, these instances were not free. It is already allocated. It is already allocated. Okay, so if you see P1 is holding the resource R2 and it is waiting for R1, which is being held by P2, which is being held by P2. Okay, and P2 is holding R1 and it is waiting for R3, which is being held by P3. Okay, and P3 is holding the resource R3 and it is waiting for the resource R2, which is being held by P1. So it becomes a circular wait. So you check all the four conditions were satisfied. Mutual exclusion. Yes, all these processes are basically in mutual exclusion because if this resource R1 is allocated to P2, then nobody else can use it. So all these are in mutual exclusion. Okay, and hold and wait. All the processes are holding a resource and it is waiting for some other resource. Okay, so the second condition, hold and wait, is satisfied, and no preemption. So generally there will be no preemption. That is, the CPU will not, the operating system will not forcibly remove any resource from any process. And the last is circular wait. So circular wait is also satisfied. So basically this graph, it actually represents a deadlock. Okay. So there is a deadlock because we have only two instances of R2 and those are also already allotted. Okay, fine. So let us see another graph with a cycle, but there is no deadlock. If you see this particular graph, here there is a cycle, but there is no deadlock. See, there are four processes: P1, P2, P3, and P4, and there are two resources R1 and R2, and each of these resource has two instances. R1 has two instances and R2 has two instances. Okay. Now one of the instance of R2 is allocated to P1 and P1 is waiting for R1. P1 is requesting the resource R1. But one of the resource of R1 is allocated to P2 and another instance of R1 is allocated to P3. Okay. And P3 is waiting for R2. But another resource of one of the resource of R2 is already allotted to P1 and another resource is to P4. Okay. But this case, even though here there is a cycle, there is a cycle from P1 to R1, then R1 to P3, then P3 to R2, then R2 to P1. Even though there is a cycle, this will not lead to deadlock. Here also the resources were not free. R2 has two instances of the resource, both were assigned. R1 also has two instances of the resource, both were assigned, but this will not lead to cycle, but this will not lead to deadlock because there is no what you call hold and wait here. There is a see P1 is holding a resource and it is waiting for another resource. P3 is holding a resource and it is waiting for another resource. But P2 and P4 they are only holding a resource. They are not waiting for another resource. Okay. P2 and P4 they are only holding some resource. They are not waiting for any other resource. So eventually after a period of time, P2 will use the say after time X, P2 will release R1. The moment P2 releases R1, process P1 will get R1 and P1 will complete. Okay. Similarly, after some times P4 will release R2. The moment R2 is released, P3 will get that resource. Okay. So this is a case where there is where there is a cycle, but there is no deadlock. Okay. So this is what we understand from resource allocation graph. That is, after drawing a resource allocation graph, if there is no cycle, then there is no deadlock. If there is a cycle, then if there is, and each of the resources only one instance, then you can confirm that there is a deadlock. But if there are multiple instances available for each resource, then there is a possibility of the deadlock. Okay, so let us stop here. Thank you.